In today's lecture, we discuss about the different types of systems. So before going for the different types of systems, let us see first what is a system. Okay, a system is for every possible input signal. Okay, for every possible input signal, it produces, or a system produce, a possible output signal, produce an output signal. Yes. So consider this one as a system represented with h of t. For a signal x of t, you will get a signal y of t. So this is the mathematical representation. Mathematical representation which gives the relation between input and output. Between input and output. Okay. So this h of t is referred to as an impulse response of a system. Impulse response of a system. Okay, and in the discrete case, this is h of n. Okay, so let us see the different types of systems. First one, starting with memory and memoryless systems. Memory and memoryless system. So what is a memoryless system? Okay, in the memoryless system, the signal output, the output depends upon, that is output y of t depends on present input. Present input, that is the output y of t naught depends only on x of t naught. It doesn't have the memory. The system h of t doesn't have this memory. Okay, this indicates that at that current instant of time t naught, okay, we are getting an output y of t naught, simply x of t naught. For example, you can take a resistor, that is v of t equal to r into I of t. Okay, and this is the voltage provided for the resistor, and I of t is the current passing through that resistor. So R is a system, that is a resistor is a system with no memory. Okay, is a system with no memory. Okay, and take another example, that is y of t equal to x square of t, x of t or x square of t. Okay, so this one also, y of t naught depends on x square of t naught, that is at present instant only. Okay, at the present instant of time we are getting the output. So this is the memoryless system, doesn't have any memory. Okay, that is y of t depends on present input only in the memoryless. In the memory system, output depends on the present input as well as the past inputs also. So the output y of t depends on present input and past inputs. Okay, So this indicates the memory of the system. Okay, so example, y of t equal to x of t minus 2. Let us consider y of output at an instant of 0, okay, time 0. So this is x of minus 2. So y of 0 is dependent on the past input. So this one is the past input. So y of 0 at current instant depends upon the, output at time 0 depends on the input at minus 2, that is past input. So this one is a memory system. Okay, this one is an memory system. The past input was considered for the calculation of output y0. Okay, and you can consider another example, v of t equal to, that's capacitor, 1 by c integral I of tau d tau. Okay, and this is also a device, that is capacitor is a system which have the memory. Okay, so capacitor is a system which have memory. So it considering the past currents, past values of I of t or I of tau. So capacitor is a memory system, and where the resistor is a memoryless system. Okay, so this is one category, and in the second one, the causal and the non-causal. Causal and non-causal system. Okay, the causal system, for causal system, the output depends on only on the present and the past inputs. Output depends on present and past inputs, but not on the future inputs. Okay, but not on future inputs for the causal system. Okay, this is example, you can take it as y of t equal to x of t minus 2 plus x of t. Okay, so this one, the output y of t depends upon the current input x of t and the past input. Okay, so next, in the non-causal, system, the output depends upon the present, past, and as well as the future inputs also. Output depends on future inputs also. So such system is a non-causal system. So important one is the causal system, output depends upon the present and past inputs. Okay, and for the non-causal, output depends on future inputs also, along with present and past inputs. Okay, so the third category, an important one, we discuss about the linear and non-linear systems. Linear and non-linear linear and non-linear systems. So a system is said to be linear when it was satisfying the properties of homogeneity and additivity. Okay, if a system is said to be linear if it is satisfying the two conditions or two properties, one is additivity and another one is homogeneity. So to be linear, the system to be linear, it should satisfy, should simply obey, satisfy two properties. One is additivity and homogeneity. Okay, so both properties should be satisfied by the system. Okay, let us check first additivity. So here we represent, we use a terminology like t of x of t equal to y of t, that is y of t is the output when x of t is given as an input for a system having a transfer function t. Okay, so first, that is a simple representation like this, x of t and y of t, you can take this t. So for the input x1 of t, if you are applying an input x1 of t for the system, you are getting an output y1 of t, and again you are giving an input x2 of t and getting an output y2 of t. Now if you apply the x1 of t and x2 of t combinedly for the system, okay, and you are getting an output y3. Now you have to check that given equations 1, 2 and 3, if y3 is equal to y1 of t plus y2 of t, then system is satisfying additivity. Okay, the system is satisfying additivity. Right, now let us check the homogeneity. The second property, so along with this additivity, now let us check homogeneity. The same, I am giving a signal x1 of t and observing an output y1 of t. So here I am giving the signal a x1 of t, that is multiplied with some constant, and if you observe an output, a y1 of t, and same you apply another signal b x2 of t and you observe b y2 of t. Okay, and the property satisfied by this, okay, if this one is satisfied, that is a x1 of t, sorry, we will discuss about this thing later, the combination of two signals. So let us consider ax of t is the input and we are observing ay of t. So we're getting this one at the output also. This indicates that the system is satisfying homogeneity. Okay, the system is satisfying homogeneity. So individually we have checked about this additivity and homogeneity. Now let us combinedly take the additivity property and homogeneity property. That is, if the system is satisfying the condition like a x1 of t plus b x2 of t, that is, I am considering another one like t of b x2 of t equal to b y2 of t. Okay, equal to a t of x1 of t plus b t of x2 of t, that is nothing but a y1 of t plus b y2 of t. Okay, if this above equations like 1, 2 and 3, if 1 plus 2 is equal to 3, then the system is a linear system. Okay, if both are satisfied, that is additivity and homogeneity, if both are satisfied, the system is a linear system. Okay, let's check for a small example for the linearity checking. The case like y of t equal to e power x of t. I am considering this example. So first y1 of t is the output for e power a x1 of t. Okay, next y2 of t is the output, that is so y2 is the output for e power a x2 of t. Okay, so y3 is the output for e power, so not this one is a, this one is b. y3 is the output when you give the inputs combinedly, that is a x1 of t plus b x2 of t. So now you check these three equations. Okay, whether y1 plus y2 is equal to y3 or not. Okay, so y1 plus y2 equal to e power ax1 of t plus e power b x2 of t. This is not equal to e power a x1 of t plus b x2 of t. Okay, so y1 plus y2 is not equal to y3. So system is not linear, non-linear. Okay, so y of t equal to e power xt, that is giving the system, giving the relation between output and input. Okay, so system is a non-linear system. Now we consider another example, y of t equal to x of t square. So y1 of t equal to a x1 of t square, sorry, again same, y2 of t equal to bx2 of t square. So y3 of t equal to ax1 of t square plus bx2 of t square. Now let us check y1 of t plus y2 of t equal to ax1 of t square plus bx2 of t square. So this is equal to y3 of t. So system is linear. It's a linear system. Okay, like this you can check whether a system is linear or not by observing or else by checking about the additivity and homogeneity. Okay, so another important system is variant systems. Okay, that is time variant or time invariant. So time invariant and time variant system. Okay, right. So it's a property of the system which makes the behavior of the system independent of time. Okay, so time invariance, this indicates that the system is, or system behavior is independent of time. Okay, this is the property of the time invariant system is time independent. Okay, so let us check that. You consider a system like this. I am giving an input x of t and getting an output y of t. Okay, so this system is producing some output, a random output. I am considering an input like this. Okay, and the system is giving an output, a random output, for example. Okay, now I am giving a delayed input signal. Okay, the input was delayed by tau. So this is x of t and this is y of t. Now I am giving a delayed signal. Okay, I am giving a delayed signal and I am getting an output, a delayed output by the same time t. Okay, so now I will apply the same delay of t for this y of t. So y of t minus t. Okay, so I will apply the same amount of delay for this output y of t. So if this is equal to this one, then the system is time invariant. Okay, so I will give the clear picture regarding it. Y of t is output for a system when x of t is the input. Okay, and y of t comma t, capital T, is the output when a delayed input was given to it. This is output for delayed input x of t minus t. Okay, now y of t minus t is a delayed output. Okay, so y of t substituting t equal to t minus t, and this is the delayed output by t. These both are different. Okay, y of t comma t is, okay, output for delayed input, but y of t minus t is delayed output. Okay, we are considering two versions: finding delayed output, okay, finding an output for the delayed input, and another one is we are delaying the output y of t by capital T. If y of t comma t is equal to y of t minus t, then system is time invariant. The time invariant, that is output due to delayed input is equal to delayed output. What was the time? But I mean the same time. Okay, delayed input and the delayed output. Then the system is the time invariant. If not, if both are not equal, that is if y of t comma t is not equal to y of t minus t, this is time variant. Okay, the time variant, outputs are getting a different outputs. Okay, this is the time variant. So let us check an example. Y of t equal to t square x of t. Okay, so first output due to delayed input, that is just input was only delayed. Okay, so x of t minus tau, input only delayed, so this one is t square x of t minus tau, not t. Now y of t was delayed. Okay, the output was delayed by t, that is t minus t whole square and x of t minus t, and this is nothing but y of t at t equal to t minus t. And if you observe, this one and this one both are not equal, so time variant is a time variant. Whenever you observe these terms t or t square multiplied with his input, obviously the system will be time variant. Okay, let's take another example. Y of t equal to e power 2 x of t. Let us check output due to delayed input equal to e power 2 x of t minus t, and we are delaying the output by t minus t, that is e power 2 x of t minus t. So both are equal. So time invariant. So like this we have to check for this variance, time variance and time invariance. Okay, and last important one is stable system. Stable system. So a system is said to be stable, okay, if the output is bounded, when the input is also bounded, that is bibostable. Bounded input, bounded output. Okay, so for the system, if you give the bounded input, if you get the bounded output, system is stable. Okay, so a system h of t Okay, for the system h of t, the stability was calculated as s equal to minus infinity to infinity h of tau d tau. This value should be less than infinity. Okay, if it is equal to infinity, this is unstable and this is stable. So for the stable system, if you give a bounded input, definitely you will get bounded output. Okay, this is not.